Okay, so here in this video we're going to continue on with finding the area between two curves. Alright, so let's start with, suppose we have y equals 2 minus x squared and y equals x. So here in this one we do not have the limits of integration. We are not given the x values from which we're going from to find the area between these two curves. So the first thing is we have to find the limits of integration by setting the two functions equal to each other to learn where they intersect. So it'd be 2 minus x squared equals x. Let's take everything to the left-hand side. Plus 2 equals 0. I don't want to factor with the negative, so I'll divide it out. X squared plus x minus 2 equals 0. Factor in at x plus 2 and x minus 1 equals 0. Always check your factoring to make sure that they combine to give you the positive x. So x will be negative 2 and x would be equal to 1. So now we need a sketch. And we're going to pick x is negative 2 and x is 1. So when x is negative 2, I can put that into either equation, here or here. So when x is negative 2, so is y negative 2. When x is 1, so is y 1. So these are the 2 points where the graphs intersect each other. So now I have to pick one more x and put that into each function so I know what the graph looks like. So if I pick an x in between, between negative 2 and 1, 0 is your easiest choice. So put 0 into this function and I get 2. Now connect it. You know that your basic shape x squared, negative x squared, is a parabola concave down. So connect it like a parabola concave down. Now if you pick 0 for this one, you also get that y is 0. So now connect these three. Draw the rectangle in the enclosed region to represent that the area between those curves is the sum of the area of the rectangles from negative 2 to 1. If you think about it, this is the continuation of that graph 2 minus x squared. This is the continuation of y equals x. And this is the area where the two graphs intersect each other, between negative 2 to 1. So the area is going to be equal to the definite integral from negative 2 to 1 of the top function minus the bottom function. So the top is 2 minus x squared minus the bottom, which is x, dx. So clean this up, and this will be from negative 2 to 1 of negative x squared minus x plus 2 dx. And then that antiderivative would be negative x cubed over 3 minus x squared over 2 plus 2x from negative 2 to 1. Let's put in the top number first. So if I put in the top number, I'll get negative 1/3 minus 1/2 plus 2. Minus, no calculator here. Do this all by hand. Negative 2 cubed is negative 8 times a negative is a positive 8/3. Negative 2 squared is 4 divided by 2 is negative 2 minus 2. Minus 4 that would be. Negative 2 into here gives me negative 4. Okay? Alright, so then now I'll distribute the minus through. I'll get negative 1/3 minus 1/2 plus 2 minus the 8/3 plus the 2 plus the 4. And that'll give me here 4 plus 4 will give me 8. So this will be equal to negative 1/3 minus 1/2 plus 8. Minus 8/3 yet. Plus 8. Negative 1/3 and negative 8/3 is negative 9/3 or negative 3 minus 1/2 plus 8. Negative 3 times 2 is negative 6 minus 1 is negative 7 halves plus 8. And then negative 7 plus 16 all over 2 would then of course leave me with 9 halves. Okay, so no area can ever be negative. That answer has got to be positive. If it comes out being negative, you either made a mistake in the computation down here, or you did not put the top function minus the bottom function. To check yourself, you can put this right here, this part, into Math 9. Or from the very beginning, you could have done it right here and had included absolute value bars around it. In case you did not have the top function minus the bottom function, you would still get the same answer then. Okay? We want to be able to get these answers without a calculator. Okay, next. Suppose we have y equals x squared and y equals root x. Alright, so we'll set them equal to each other. And the best way to undo the square root is to square both sides. So it'd be x to the fourth equals x. Set it to 0. Factor out an x. And I will have then, if I square both sides, I get that. So I'll get factor out an x squared. Yeah, I don't know why there I had x squared. So when I square both sides, I do get this. Okay, I have an error on my paper. Okay, so then I set this equal to this, square both sides to undo the square root, and yes, I was right. So I'll get here, no, I'm squaring both sides from here. So now I get x to the fourth equals x, set it to 0, take out an x, and x would be equal to 0, or x would be equal to 1. Okay, so then now when x is 0, put that into either one, doesn't matter, y will be 0. Pick x as 1, put it in, I get y is 1. There it is. Now you have to pick an x in between these. So you pick your limits of integration and you pick an x in between. So I'm going to pick something I can take the square root of, like a fourth. So if I pick x as a fourth for this function, I'm going to get y to be 1/2. So over a quarter up a half. And we know that the square root function looks like this, is its shape. Now, sometimes it pays to pick the same x for this function, so you can compare the y values. So if I pick a quarter for this function and square it, I get a 16th, which is smaller than 1/2. So that's down here. And what that tells me is, between 0 to 1, this function, the x squared, is below the graph of y equals root x. And root x is on top. So this is where the two graphs intersect. Draw the rectangle in between them to indicate, the area between the two curves. So that area is going to be equal to the definite integral from 0 to 1. Since the rectangle is drawn vertically, the height of each rectangle is the top minus the bottom. So the top function is root x, the bottom is x squared, close it, dx. Now take the antiderivative of each piece. That would be x to the 3/2 times 2/3 minus x cubed over 3 from 0 to 1. Putting in the 1, you'll get 2/3 minus 1/3, which leaves us with 1/3. And of course, minus the 0 in this case is just going to leave us with 0 for that. Okay, so the biggest thing is we have to know what function's on top, what function's on the bottom. Remember that this here, this alone, represents the area of one rectangle. This is the sum of all those areas. This right here is the height of one rectangle. It's the top y minus the bottom y. The top function minus the bottom function. This is the width of each rectangle. This right here is your delta x. This is the height. And when you multiply these two dimensions, you get the area of a rectangle. And this here would mean the sum of all those areas. Okay? And let's do one where we have something going sideways, where it's not a function of x. So suppose we have x equals y squared and x equals y plus 2. So here in this one, what's different is the y's are squared maybe or cubed. So in that case, you want to solve them for x. Okay, these are going to be functions of y's and not of x's. So what I'm going to do is, since x equals this and x equals this, I'm going to set this equal to this over here to find out where they intersect. So it'd be y squared minus y minus 2 equals 0. Factor y minus 2 times y plus 1 equals 0. So y is 2 or y is negative 1. So everything gets reversed, meaning that now these are your y values. So let's go. Okay, so when y is negative 1, you can put it back into either spot to learn what x is. So when y is negative 1, I get x to be 1. So 1, negative 1. When y is 2, I can put that here and I get x is 4. 1, 2, 3, 4, up 2. Okay, now, this time, since the limits of integration are in terms of y, pick a y in between each graph. Pick a y. So then if y is 0 for this graph, if y is 0, I get x is 2. So 2, 0. Now once you have that third point, connect them. Well, this is a line. We could solve that for y, and it's y equals mx plus b. So connect it like a line. There it is. Now, you can also pick here, if I pick y is 0 for this graph, I could do that. So if y is 0 for this graph, I get x is 0. Now how am I going to connect it? Remember, this is where the graphs intersect. So I have to pass through those 2 points for that graph. Now using this third point, I got to connect through these 2 x's and include that third point. Well, when you have a positive y squared is a parabola sideways opening to the right. This is a positive y squared. A negative y squared reverses it the other way. So positive y squared will get swung this way. Now, when these are solved for x, because it's easier here to solve for x, we could actually solve these for y, as you'll learn coming up, and do these by solving them for y, but it will take longer. So it is easier here to solve both of these for x, because they're already solved for x, or it may have been easier to solve them for x. So then we'll do everything in terms of y. So when these are solved for x, and your limits of integration are in terms of y, when the limits of integration are in terms of y, the rectangle will be sideways. And now the height is your dy. How high this is dy. And your width of that rectangle will be the difference in the x's, which are functions of y's. So it's going to be a right minus a left to get the width. So the area is going to go from negative 1 to 2. And again, because the rectangle is drawn sideways, you're going to go right minus left. So the function on the right is y plus 2. And the function on the left is y squared. And you can close it dy. So again, so you understand what you're doing, this here is now the width of each rectangle. The width of this is the difference in the x's, the difference in these, but the difference in the x's are functions of y's. And the height here is the dy. So this here, if we clean it up, is negative 1 to 2 of negative y squared plus y plus 2 dy. And let's take that antiderivative to get negative y cubed over 3 plus y squared over 2 plus 2y from negative 1 to 2. Put in the top limit first. I'll get negative 8/3. 2 squared is 4 divided by 2 is 2 plus 4 minus negative 1 cubed is negative 1 times a negative is a positive. Negative 1 squared is a positive 1/2 minus 2. And then now distribute negative 8/3 plus 6 minus 1/3 minus 1/2 plus 2. And then this here will give me 8. That gives me 8. Negative 8/3 and negative 1/3 is negative 9/3 or negative 3 minus 1/2. And this here will give me negative 3 times 2 is negative 6, minus 1 is negative 7/2, plus 8 will give me here negative 7 plus 16 over 2, which is 9 halves. So that comes out there to be 9 halves. Okay, and I'll do just one more. In some of the cases, if you're given the limits of integration, you can just use those. Okay, so suppose here x equals 3 minus y squared, and x equals y plus 1. So let's set them equal to each other. Notice they already solved for x, so therefore, when our limits of integration are in terms of y, it's a sideways rectangle, sideways. So then now, take over everything, minus y minus, that's going to be plus 2. So I'll have negative y squared minus y plus 2. Divide out the negative to get that. So I'll get y plus 2 times y minus 1 equals 0. And y is negative 2, or y is 1. So again, make our sketch. Okay, so now I pick y is 1, and x is 2. Over 2, up 1. And when y is negative 2, I'll get negative 1. So negative 1, negative 2. So those are the points where the graphs intersect. Pick a third point. Pick a y in between. If these were x's, I'd pick an x in between. Since these are y's, then I'll pick a y in between, like 0. So if I do this one, I get 0 plus 1 is 1, so I'll get 1, 0. Well, this is a line, so connect it like a line. I could still pick y as 0 for this one. When I do that, I get 3 for x. Y is 0, so I'll get 3 for x. Because it's a negative y squared, it's going to be a sideways parabola, but in this direction, right there. And because my limits of our integration are in terms of y, it's a sideways rectangle, like that. So the area set up will go from negative 2 to 1 of the right function minus the left function. When it's sideways, it's right minus left. When the rectangle is vertical, and the limits of integration are in terms of x, it's top minus bottom. So on the right will be 3 minus y squared minus the one on the left, which is y plus 1 dy. So clean this up. 3 minus y squared minus y minus 1. And that's negative y squared minus y plus 2. So definitely clean it all up before you start taking the antiderivative. So this would be equal to negative 2 to 1 of the function negative y squared minus y plus 2, close it, dy. And that antiderivative is negative y to the third over 3 minus y squared over 2 plus 2y from negative 2 to 1. And if you put those limits in and do the math, which I'm not going to do in this case, the answer would be 9 halves. Okay? And as the examples we did in class sometimes is that if you are given the limits of integration already, then just use them. Then just use them already. We had some cases like where we had y equals e to the x and y equals x. Well, these are not going to intersect. And we had x be equal to 0 and x be equal to 1. So in that case, these are your limits of integration. So in drawing that graph, you pick the ends. E to the 0 is 1, and 1 is e, which is 2.718, which is up here. Connect it like its shape. And then when you pick 0 for this one, you get 0. And when x is 1, you get 1 for this one. And it's a line. So sometimes the graphs have no intersection, but we can still find the area because they're bounded by the lines from x equals 0 to x equals 1. Well, x equals 0 is a vertical line right here. X equals 1 is a vertical line right there. So the area is bounded by all 4 of these. So since these are solved for y, draw the rectangle vertically. So the area of this region would be equal to, from 0 to 1, the top function, which is e to the x, minus the bottom function, which is x, dx. And that antiderivative would be e to the x minus x squared over 2 from 0 to 1. And then you be careful here, this would be e minus a half minus e to the 0 minus 0. But e to the 0, don't forget, is 1. So this here is e minus 3 halves, because this right here would be 1, and this would be negative 1.5. But this is still positive because e is 2.718, which is greater than 3 halves. So it's still a positive area. Okay, so again, in some situations, the point here being is you are already given the limits of integration. But what are the graphs of these? These are vertical lines. X equals 0, x equals 1. So the area is bounded by all 4 graphs. And there is no intersection, but we can still find that area. So if the limits of integration are given, use them. If not, then set the equations equal to each other to find out where the graphs intersect. And they will be your limits of integration. And once again, if the rectangle is vertical, it's a dx. It's the top minus the bottom. If the rectangle is horizontal, like this, it's a right minus the left. Okay, so when the limits of integration are in terms of y, it's a right minus the left. When the limits of integration are in terms of x, it's a top minus the bottom.